Today I am discussing about Bose-Einstein statistics. The properties of Bose-Einstein statistics are: these statistics apply to particles which are identical and indistinguishable. Spin angular momentum is 0 or integral multiple of h by 2 pi. They do not obey Pauli's exclusion principle, so they can stay in any quantum state or phase cell. Here the sum of energies of all the particles in various quantum states is equal to the total energy of the system. It is also assumed that the number of phase cells is comparable to a number of particles in the system, that is Ni by Gi equals 1. Consider an isolated system consisting of weakly interacting particles. Total number of particles be n and has a volume v. The system is assumed to be in equilibrium at a temperature T and its total energy E, which is a constant. We have to find maximum probable distribution of the particles in the phase space. For this, the phase space is divided into a large number of quantum groups, and this is again divided into phase cells of volume h cube each. Let n1, n2, n3, etc. Ni be the number of particles with energy E1, E2, E3, etc. Ei respectively. n1, n2, n3, etc. are called the occupation numbers of the levels, and the number of phase cells Gi in an energy level Ei of ith level is called degeneracies. The degeneracy is also called statistical weight of the ith level. n1 plus n2 plus n3 etc. plus ni equals sigma ni equals capital N, a constant. The total energy of the system is ni n1 e1 plus n2 e2 plus n3 e3 etc. plus Ni equals sigma Ni Ei equals capital E. The total energy is a constant. Distribution of Ni indistinguishable particles among Gi distinguishable levels. For this, Gi minus 1 partitions are necessary. Thus, Ni particles are to be arranged in a row distributed among Gi quantum states with Gi minus 1 partitions in between. Then the total number of possible arrangements of particles and partition is equal to the total number of permutations of Ni plus Gi minus 1 particles in a row. Hence, the total number of possible ways of arranging Ni particles with the Gi minus 1 partitions equals Ni plus Gi minus 1 factorial. But since the particles and the quantum states were indistinguishable, we have to deduct Ni factorial ways and Gi minus 1 factorial ways from the all possible ways to get effective number of arrangements. But the particles and the partitions are identical indistinguishable, so these permutations would not give any independent arrangements. Hence, the number of independent permutations of Ni particles among Gi states is Wi equals Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. We can derive similar equations for other energy groups also. Hence, the total number of W of independent ways of arranging n particles in various quantum states is given by W equals W1 into W2 into W3 etc. That is Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial into N2 plus G2 minus 1 factorial divided by N2 factorial into G2 minus 1 factorial into etc. That is pi I into bracket Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. Thank you.